SMJP 1022 Material Science, Chapter 7 Carbon Steel. In this chapter, we will cover part B, which is the final part of our topic, and this is the last part of our course, which is heat treatment of steel, time temperature transformation diagram. In this part, we will cover heat treatment, various types of heat treatment, and then we go through time temperature diagram, and also we covered alloy steel, and finally we have a cast iron. So for the heat treatment, actually we studied of heat treatment due to the change of heating and cooling, and from there the material we will alter for the physical and mechanical properties, and then we can gain information of machinability, grain structure, tensile strength, internal stress, soften the metals and hardness of metals. This is the information that can be gathered from the doing the step of in the process of heat treatment. Actually, the objective of heat treatment is to strengthen the material, harden and wear of resistant, especially for bulk hardening and surface hardening, and then to increase ductility and softness. This is in the process of tempering, recrystallization, annealing, and also to increase toughness, to obtain fine grain size, especially in doing for the process of annealing, full annealing, normalizing, and then to remove internal stress induced by differential deformation by cold working. Previous part we already learned about cold working process. Non-uniform cooling from high temperature during casting and welding. There are three major stages in heat treatment. Actually, we will cover the stage one, which is heating. So we heat metal slowly to ensure at a uniform temperature, at the desired temperature actually. So and then go for the second stage, which is soaking, whereby the temperature of the metal is whole at a certain given temperature and time, and then to make sure that the component is equated between the surface and its core. So that's mean the sample or the metal will 100% in the temperature. So the last stage, which is the stage number 3, which is cooling. So that in this stage, the sample is cool to room temperature. Okay, this is done by put in the furnace by switch off the furnace and let the temperature start to cooling down, and by leaving heat treated material to be cool in the certain medium, so that we let the air put in the air condition, and then put in the oil or dip in the oil, and or put in the water to make it cool. Yeah. All heat treatment basically the process are similar. Okay, different process of heat treatment basically similar because of all involve the heating and cooling of metal. and there are difference in method, okay, such as heating temperature at a certain degree temperature, and cooling rates, maybe slow cooling rate or fast rate, and the quenching media, okay, such as water, oil, okay, necessary to achieve a desired properties. All those things basically to alter the properties. The heat treatment of ferrous metal in this topic basically usually consists of four basic types of heat treatment. Okay, the number one is annealing, and then we have normalizing, quenching or hardening, and finally we have tempering. So we have another two, which is Mars tempering and Aus tempering. This is the step of uh, the advanced or modified method of tempering. So the type of heat treatment basically, if we can see from the uh, view of many types, okay, which is the purpose of the process basically for the normalizing, which is to refine grain structure and then increase strength. For the quenching, basically to increase hardness. For tempering, basically to reduce brittleness, increase ductility, remove internal stress. And for annealing, basically to soften the materials, especially steel, and to refine grain size, and also to relieve internal stress and alter magnetic, electrical, and physical properties. And for another tempering and mild tempering, there is a modified quenching process, which is to alter the procedure to conventional quenching and tempering. So we will discuss on the annealing. So the objective of the annealing is basically to soften the material or soften the steel, especially the opposite of hardening. So once we have the material is quite hardened, and then we want to manufacture, okay, by using equipment, so that is we need to have a soft steel. So by annealing, we can make the material soften it in the for easy cold working and machining. Refine grain size to improve mechanical properties in terms of strength, ductility, and toughness. Okay, the objective is to relieve internal stress caused by the plastic deformation process. Basically, we can for the non-uniform cooling of a component fabricated at high temperature. And then for phase transformation, parent and product phase have a different density. It is also to alter electrical, magnetic, and physical properties. And as a result, we will remove the trap gas. And type of annealing process, actually we have a full or complete annealing, and then we have a process annealing and spheroidizing annealing. But in this case, we will look at the differences between full annealing and process annealing. But a lot of type annealing process available, so we just to know the difference between full annealing and process annealing. For the full or complete annealing, the objective is to soften the material, and we can get a refined grain structure, at the same time relieve stress and remove trap gas. The process is basically heating the sample metal between to 25 to 50 degrees Celsius above critical temperature. It's for the hypoeutectoid steel, and for the hypereutectoid steel, the heating process is 50 degree above lower critical temperature. And then after heating at this temperature, we will hold the temperature in the soaking process, which is to achieve the equilibrium about 3 to 4 minutes. Okay, for that the all sample is in the equilibrium of the specific temperature, and then start to cooling down in the furnace. For this full complete annealing, we let the sample is cooling very slow at a certain several hour will take place. And the product in terms of microstructure, we will get the coarse perlite, okay, perlite, and then we have a small and uniform grains. And for the we have a soft and ductile. This is suitable for the machinability. Okay, and then for the process annealing, the objective is the same, to soften and increase ductility in the previously for the cold working metals and the relief stress. Okay, the process takes place when we heat the sample at above 500 degrees Celsius above until 650 degrees Celsius, whereby the crystallization temperature for the low carbon steel is about 500 degrees Celsius, which the process is the recovery and recrystal process takes place. And then complete in matter of on the reaching maximum temperature, and the products basically increase ductility, and at this place the phase is no change. Fine grain microstructure develop. Okay, stop process before grain growth occur. Surface oxidation minimize. Okay, in this condition we have a very low heating temperature and non-oxidizing atmosphere. Okay, for the application, we have a low carbon steel. Okay, where we produce mild steel. Okay, during extensive plastic deformation, and will allow a continue of deform without a fracture or extensive energy consumption. And this is application for sheet and wire production. And then we go for the normalizing. Basically, the objective of normalizing is harder and stronger steel, but it's less ductility for the same composition. Okay, if we compare to the full annealing. Okay, the process basically remove the external stress, okay, and then induced by heat treating, welding, casting, forging, forming, or machining. Uncontrolled stress lead to metal failure. Okay, therefore normalizing of steel before hardening it to ensure maximum result. It is often used for ferrous alloy that have been heated to a higher temperature. Okay, whereby we heat at the higher temperature at the face of arsenide and then cool in open air. Normalizing not only produce perlite, okay, perlite, but also bainite and some of we call it martensite. Okay, in normalizing, since the metal is air cooled, the mass of the metal has a significant influence on the cooling rate. Okay, and hence on the resulting piece hardness. So with normalizing, thin piece cool faster in the air and harder than thick one. So we compare the metal in a thin piece and thick one. So the thin piece is very hard than thick one. Okay, during the normalizing, whereas with annealing and its associated furnace cooling, the hardness of the thick and thin pieces is about the same. Okay, if we compare with the process of annealing, the thin and thick sample is about the same hardness. And for the stress relieving, basically is a technique to remove or reduce the internal stress created in metal and produce material a uniform fine grain structure. Okay, this stress actually caused in a number of ways, ranging from cool working to non-uniform cooling. Stress relief is usually accomplished by heating a metal below the lower critical temperature and then cooling uniformly. And then for the quenching or hardening, the objective, as the name of hardening, is to harden steel, but also to increase its strength. And the process of quenching, basically process of cooling a metal in the rapid rate. The process is the same as previous, but the step of cooling, basically we make it cooling very fast. So a metal cooling a metal at a rapid rate. This is most often done to produce a martensite transformation. Okay. Okay, by hardened by quenching a metal, usually steel or cast iron must be heating first at the upper critical temperature and soaking, and then start to cooling down. Okay, the several process for the cooling can be done by using forced air or other gases such as nitrogen to make it the cooling rate is very fast, and or we can use a liquid by dipping due to the better thermal conductivity such as oil, water, polymer dissolved in water, or a brine, which is a high concentration solution of salt in water. In ferrous alloy, basically often produce a harder metal, okay, for the quenching. And for non-ferrous alloy will usually become softer than normal. Okay. And then for the tempering is the process of can be done when the material have been quenched. Okay. Uh, to its hardness state, and then we proceed to use a tempering process to achieve a greater toughness and ductility by decreasing hardness. Okay. In this figure, you can see the first of we heating at the austenizing up to alternizing, and then we make a quenching process, and the next part we do a part of process of tempering. This is the tempering process. Okay. Okay, tempering is achieved by heating the quench material to below the critical point for a set period of time, then allowing it to cool in still air. Both of the temperature and heating time depend on the composition of metal. Okay, and will determine the amount of hardness removed. So the parameter such as composition, the time, the temperature, so it will determine the amount of hardness. Okay. Okay, benefit of quenched and tempered plates, so we can become less brittle and more ductile material, so without sacrificing too much hardness. So that it will produce a less brittle and more ductile uh, material. It is the combination of these two processes that produce a harder, tougher steel that more weldable and ductile than ordinary carbon steel. And then we go for the time temperature transformation. Basically, we already covered in part A, which is we have the carbon steel phase diagram. So in this part, we will the information of carbon steel basically, but not in term of time temperature transformation diagram, uh, phase diagram, but also we can produce a time temperature transformation. In this case, we will go to analyze the diagram, and we can get many information from there. So the TTT diagram basically is a plot of temperature versus the logarithm of time. So we have a set of time from 0 to certain time, that in term of logarithm. So we can see a graph changes of the temperature and also time for a steel alloy of definite composition. TTT diagram indicates a specific transformation start and end, and it also show what percentage of transformation of austenite at a particular temperature is achieved, so that at a certain uh, composition, and then we can see a transformation of material in term of transformation of austenite, okay, with the percentage from 0% to 100%. Okay, with the graph of we have a start and ends graph. So after this we will see. So if you see from the right left hand side graph, you can see there is a two line curve here, okay, like this, and then we can see start here, and also that we have a second curve here, and it will have a uh, final or ends. Okay, start is 0%, and we have the final, the end is 100%, supposed to be 100% here. In the middle, basically, the 50% of transformation takes place in the middle. So from there, we can analyze of the temperature different, okay, at a certain temperature at eutectoid temperature, and what will happen to the phase of uh, phase diagram. So in term of austenite transform to pearlite to other form of phase. Okay. The, the aim of TTT diagram is determine type of structure for the portion in the curve and to obtain the specific properties. And it also called the isothermal transformation diagram. Okay, the transformation of austenite, which is gamma, at a constant temperature, and then heating from room temperature to austenite region, okay, which is at the eutectoid steel, which is as you can see at the line in red line here, which is the eutectite steel, the composition of 0.8% carbon, and then soaking at a constant temperature, and then cooling rapidly to a temperature low eutectite temperature. Okay, as you can see here, we have the eutectite region at a higher temperature at 723 higher. So this is the austenite region, and then we set for the cooling rapidly, and it will go for the rapid cooling temperature, okay, below eutectite temperature, okay, here in this area. Okay, and then the austenite basically transform to pearlite, okay, which is the composition of ferrite and cementite here. Okay, so from here austenite we transform directly to pearlite, which is composed of ferrite and cementite. Basically, time temperature transformation diagram is a curve produced of the uh, temperature versus a logarithm of time. Basically, as you can see in this diagram, okay, it's kind of a S-shaped curve of percent of austenite. Okay, austenite. Okay, the transform to pearlite, whereby the austenite transform to pearlite, which is consists of ferrite and cementite. Okay, we can get the information of rate of transformation. You can see the increase rapidly at the beginning and decrease by the end, so that the time and temperature depend on transformation can be represented by the plot of temperature versus logarithm of time. Okay, two curves are plotted. Basically, we have a left curve. Okay, left curve is the time required at each temperature for the start of transformation, which is this left curve here. Okay, indicates the start of transformation, and then we have the right curve, which is here, time required to end of transformation. Okay, and this line is indicated in this line, and we have in between, which is 50% of progress of transformation. Okay, and then we try to analyze the transformation of austenite at a constant temperature. Okay, basically we will look at the eutectoid temperature, which is this line, okay, at the 723 degrees Celsius. Okay, so in this line, basically uh, if we can see on the left line here, is indicates of the curve of austenite, which is the face of austenite here. Okay, this section. So the right of the transformation curve, okay, from here to here, we have the end of transformation, which is 100% of a completion curve. Okay, the austenite we transform to another phase, we whether the pearlite or bainite or something. So, and then we have the pearlite or bainite. In this region, we have two phase. We have pearlite and bainite here. It depend on the uh, temperature range or temperature, a certain temperature at certain temperature. Okay, in between, which is the mixture of the austenite and pearlite or bainite here. Okay, and then we have the two curve, which basically in C shape. So the term they call it nose. Okay, so we have when we want to analyze, we have a faster rate of transformation and slower rate of transformation. For the faster rate of transformation, which is at the nose of the curve, okay, here the transformation is very fast, whereby if this cross intersection is 550 to 500, let's say 510, the time is very fast here. If we look at the slower transformation, is above and lower. Let's say from 723 to 600, the time is take quite some time to reach at 600. Or if we look at the below, so the curve is very long, so it will indicate the slow transformation, or we have the rate of transformation is very slow. And for the transformation between 723 degrees Celsius to 535 degrees Celsius, we indicate in this line, okay, this line and this line. So as the same as the previous diagram. So here there is a produce of microstructure of perlite. Okay, this region basically upper 535 to 723. This is the perlite or perlite region, where at the temperatures just below you take white temperature. Okay, this below this line. Okay, the transformation is basically a very slow. So the indicates the quartz perlite produced, and in terms of diffusion rate are very high, which is the C atom can diffuse long distance. So and it finally will produce a lamella in of cementite is very thick here. So with the decreased temperature, grade the transformation get faster. Okay, from here very slow rate, and then it become the higher rate in this area. So and then we can see the fine perlite produced, and the diffuse rate is decreased, which the thin lamella is produced. Okay, in this section. Okay, so later on we will see the transformation between 535 and below. Okay, in this slide we discuss on the transformation between 535 and 260, whereby we can see the curve start to bend in something like this. Okay, until this temperature. So here we can see the microstructure of bainite produced, whereby we have here in this section. So that diffusion process medium cooling. So we have the similar to perlite process basically. Phase in between actually the existing of perlite and martensite. Okay, the stronger and harder than perlite. Okay, here, and ductile and tougher than martensite. Okay, the properties of the material. The structure is very fine. Okay, and form a needle or plates in this microstructure. Okay, we have two type. The first one is upper bainite, the microstructure like a needles, and the lower bainite. Okay, we have a microstructure like a plates. Okay, upper bainites basically form a particle in alpha matrix. Okay, for the lower bainite, which is plates between 350 and 250 in this here until here. Okay. Okay, the fine Fe3C particle in alpha matrix. Okay, this is the combination of curve, which is indicates the transformation state from the 0% to 100%. Okay, in this line. Okay, if we determine the temperature line here, so during the cooling takes place from the 0% until to 100% from the austenite to produce a perlite or bainite. Okay, so we can set all specific temperature, and then we can make a cross section and we make a projection until and then we can discuss on the microstructure produced from the starting, middle, and final, or at the end of the cooling process. Okay, in terms of microstructure produced. So we can basically conclude that the process of the from the time temperature transformation, which is from the austenite, it will produce perlite, okay, plus which is the alpha Fe3C plus the pro-eutectoid phase. By having this perlite, we will do a slow cooling process. In the moderate cooling, it will produce bainite. If we use a rapid cooling, basically it will turn the austenite to martensite. Okay, and then we make a reheat, or we make a tempered the process after the quenching process. It will produce a tempered martensite. Okay, what happened to the temperature below than 260 degrees Celsius and lower? So in this section of temperature, we have the production of microstructure of martensite. Okay, so the fusion process, medium cooling, uh, through if you through a rapid cooling. Okay, and the transformation begin from beginning and start the martensite at starting here, martensite. Okay, and then we have in the middle, which is 50%. Okay, and then this line, if we have a 90% of martensite. Okay, whereby the austenite change to transformation of to be a martensite. And then we have the horizontal and linear line, the transformation of independent of time. Okay, whereby we can see the function of temperature only. Okay, the presence of alloying element and content of carbon. Okay, the change position of shape of curve shifting to the right. Okay, actually when we increase the carbon content, the nose basically we will change to the right. Okay, due to uh, composition and effect of uh, the cooling time. Okay, and then we will the formation of the separated binite nose. Okay, here. Okay, we'll change to the right. Okay, critical cooling rate that doesn't cut the curve, will produce 100% of martensite. Okay, to the left of curve rapid cooling. Okay, so another process of the heat treatment, we have mud tempering and also aus tempering, which is the process of for the mud tempering is mud quenching process, which is the modified quenching process, which is the objective of the mud tempering is basically to produce a martensite phase. Okay, to minimize a distortion of crack. Okay, so the process is developed during uneven cooling. Okay, so during the process of um, producing distortion and cracking, for that tempering will suit to avoid this kind of happen. Okay, the process is basically to austenizing the steel. Okay, and then quenching in hot oil or molten salt, and slightly above or below martensite start temperature. Okay, here like this. So that we can see two curve. This one is surface and center of sample. Okay, at below the starting at the just upper the starting, the all the surface and center is basically at the same temperature. Okay, and holding in quenching medium until a certain temperature. Okay, and stop before bainite. Okay, where the austenite form to bainite, and then cooling at the moderate room rate to room temperature. This is to prevent a large temperature difference, followed by the conventional tempering here. Okay, follow the conventional tempering, and it will produce a tempered martensite. Okay, for the microstructure, okay, martensite, if subsequently tempered, okay, and it will produce a tempered martensite here. For the mechanical properties of this process, basically, tempered and tempered steel has a higher impact energy value than conventional quenching and tempering steel. And for the austempering, the process is the same at the beginning, and the transformation process it happen in this line and to produce bainite actually. Okay, an alternative procedure to conventional quenching and tempering. The objective is basically to increase toughness and ductility. Okay, the process is first the same thing, austenizing the steel, and then quenching in molten salt, bars or lead bars at temperature just above martensite start temperature. Okay, the same as the previous martensite. Okay, and then holding the steel in the quenching medium, holding. Okay, and then at a low transformation, austenite transform to bainite here, and then finally cooling to a room temperature, and it will produce bainite. Okay, and for the microstructure of bainite produced, and the advantage of this process is basically better ductility, impact resistant than conventional quenching and tempering, and decrease distortion of quenching material. For the disadvantages, need special quenching medium, which is the medium that we use very special. Okay, and used for limited number of steel. Okay, small and thin component. And then we go for the hardenability. For the hardenability, basically, this is very useful because of uh, uh, previously we learned about the hardness test. Okay, by a different of Rockwell, Vickers, or many technique to identify the hardness of materials. So in this section, we will discuss on the uh, heat treatment process of the which is the Germany and quench process along with this hardenability. Okay, and then we make some analysis on the different parameter using uh, which is many parameter that involved in term to make a material harder. Okay, defined as property which determine depth and distribution of hardness by the quenching treatment. Okay, ability of steel to form martensite. Measure of depth to which a specific steel alloy may be hardened. Ability of alloy to be hardened by formation of martensite as a result of quenching. Okay, hardness determine the extent of martensite transformation. Okay, measure the hardness is by the Jomini and quench test. Okay, so we will discuss more on the Jomini and quench test. Okay, basically the Jomini and quench test used to measure the hardenability of steel. So the process is basically use the specimen of the standard specimen actually, but using a cylinder bar uh, at 25.4 mm, basically used in the inch, 1 inch, 4 inch long. In diameter is 1 inch, and for the length is for the 4 inch. The process is basically we heat the sample at the austenitzing specimen, whereby at a certain temperature for the specific of time, and then after removal from the furnace, and then quickly put in the fixture is something like this. In this diagram, we hold at this specimen like upside down here. So the schematic diagram is something like this, and then we have a nozzle, and then we start to set the water, heat the end of the sample, something like this. The end of the specimen is splashed by the jet of water, okay, at the temperature and flow rate determine the specific value. And then after cooling to the room temperature, flat surface is ground at a certain depth along the specimen length. Okay, later we will see. So the specimen is basically round in cylinder, and then it will make it something like this. Okay, and start to do a hardness test. So the Rockwell C hardness measurement made along specimen at the first 50 mm. Basically, there are two set of measurement. The first one is measured at every 1.6 mm. Okay, start from this point, 1.6, 1.6, 1.6, 1.6 at several interval length. And then next measured at every 3.2 mm. Okay, here 3.2, 3.2, 3.2. Okay, and finally the hardenability curve is plot, whereby the harden versus distance from quench end can be produced is something like this. Okay, we have hardness, okay, value increase, and then from the distance from the end quench, basically distance from the nozzle, this end, okay, to this, okay, for the distance, whereby in term of mm or in term of inch. Okay, so the process of the Germany and quench test is something like this. From the first step, we set the sample upside down, something like this, and then set the splash of water, and we can see the cooling takes place at a certain distance. Okay, from here start cooling process, and finally until this end of rod. Okay, and finally the specimen is basically obtained in something like this, and then we ground it as flat as possible, and then start to do a hardness test. Okay, and then this is the indent takes place from the hardness test, and from there it will produce a graph is something like this, whereby the hardness curve produced. As you can see, the hardness is at a certain length is flatten and start to decrease along the when the distance from the quench end is bigger, higher. Okay, we can get information from the cooling rate. Basically, maximum at quench ends, the cooling rate is very fast here at the end. So, and then maximum hardness is 100% martensite. And this is the 100% martensite produced. Decrease with distance, whereby when the distance is increased, the cooling rate is decreased, along with the hardness also decrease. You can see here decrease, whereby the C diffusion can occur. Okay, highly hardenable steel will retain large hardness value for a long distance. Okay, can also relate other information we can get from this hardness, time, temperature. Okay, we can get the hardness to cooling rate. Okay, rather than the distance. Here we have the graph of hardness versus distance. Also, we can produce hardness versus cooling rate, the time. Okay, and also a distance and continuous cooling transformation. Okay, or CCT diagram. In this case, we not much discuss more on the CCT diagram. And also for cooling curve for the Germany distance and resulting microstructure. So we can see cooling curve produced at a certain distance. Okay, or we can also analyze from the different technique of quenching by using water, oil, or something. It will produce a different curve. Okay. Okay, for the hardenability of 5 different steel alloy. In this case, we compare 4 different type of alloy steel, which is the uh, carbon composition is different. Whereby we uh, also we have the same composition of carbon, but different uh, content of other material elements such as molybdenum, Cr, nickel. Okay, so it will produce a different type. Okay, as you can see, there is a number 104404140. This is the classification of specific of steel, different. Okay, whereby is produced by the American Iron and Steel Institute, uh, or Society of Automotive Engineer, which they set the classification and the specification of steel. Okay, as you can see, when we plot a hardenability curve, okay, whereby we have the different composition of material in one graph, so that we can see there is a hard, hardening of material is different. Okay, as you can see, as the material of 10440 is something like this. So you can see from start from here is has a low hardenability. Okay, as the longer distance, and we have the hardness drop very quickly. Okay, as uh, we compare to the 4340 here is very stable hardenability hardness along from the very near to the far distance. Okay, so as you can see, of the different the same carbon composition, but the different element of alloy will set a different hardness. Okay, the influence of cooling rates on microstructure. Okay, at the end, quench end. Okay, the cooling rate is very high, basically around 500 degrees Celsius per second, which is in this uh, near to the nozzle. And at this area, the microstructure is the 100% martensite. Okay, at the distance of 6.4, basically distance from something like this. This okay, this line, we have the cooling rate is start to reduce at 70 degrees Celsius per second, whereby at this distance, the formation of perlite, okay, plus alpha at 1040. Okay, and for the other alloy, the formation of martensite and bainite and this distance. So as you can see here, the formation of curve or something like this. So the presence of other elements such as nickel, chromium, molybdenum, okay, it will delay the austenite to produce a perlite of or bainite. Okay, This allow martensite to form more greater hardness. Okay, in here. The factor affecting hardenability, basically there are many parameter affected. The first one is C content. Just now we already look at the C content of 0.4 carbon content. So, and what happened to the when we put the other element, the hardenability of the material will change. And also we have the alloy content effect, quenching medium by using salt, we medium of water, oil, we can give a different harden ability, the specimen size, okay, whether the rod is diameter different, okay, 50 mm, 70 mm, 100 mm, we will even though the length is the same, it will produce the different result. And also the specimen geometry, which is the specimen in shape, in term of cylinder, in term of various shape, it will produce a effect also. And we have the carbon content. The first we try to look at the carbon content. So the hardenability increase when C% increase. Okay, here as you can see in this diagram, we can see increasing of 0.6 carbon content if compared to the this value of 0.2. So the hardenability start to increase, okay, when we increase the carbon content. Okay, as you can see, the hardness increase with the C concentration. Okay. Okay, for the alloy content, hardenability increase when the alloying element added. So the even though we set the previous slide, we have the 0.4 percentage of carbon. So when we add different element, so it will produce a different. Okay, in this case of uh, alloy, different alloy, we have this different code of alloy, it will produce different hardness. Okay, which is in this case we have the content of nickel and ICMO 0.2 to 2 weight percent. Okay, and basically if we manipulate the element added here, the uh, time temperature transformation, we will move to the right here. And what happened when we change the quenching medium, okay, whereby the quenching medium is basically can be many things such as soda, brine, cool water, warm water, mineral oil. Okay, so that the basically the rapid quenching is equivalent to severe quenching. So higher cooling rate is depend on the heat energy extraction due to the different medium. Okay, so the order of the very quick quenching process is from the uh, as you can see from the quenching speed. The first is soda, second brine, uh, third is cool water, and finally in air. Okay, so if we compare to the effect of quenching medium, the effect of medium, severity of quenching, and hardness, for the three medium, which is air, oil, and water, as you can see, for the air is very small severity quenching, and for the hardness produce is very small if compared to water. Water is very uh, fast cooling rate, so they will produce a very large severity and hardness. And for the cooling rate versus diameter of bar, okay, and then basically we can see that diameter of bar, okay, as the versus the equivalent distance from the quenching ends. Basically, you can see this is the diameter of bar. As we can see, a dot produce of red, blue, green, yellow color indicate in this line. So for the diameter surface, it's radius of tricorder. We have the surface, okay, and then we have tricorder of radius, and the center of radius is basically can see a graph, a curve is produced with something like this, okay, from the diameter of, and then for the distance from the quench end. Okay, for the quenching, mildly aggregated water and oil. Okay, factor to consider in selecting quenching medium, basically whether using splash point, viscosity, chemical stability, also the main reason for the uh, for the cooling rate. Okay, and for the specimen size, okay, here we can see two specimen size in diameter. Uh, when we have the 50 mm versus 75 mm in diameter, happen when during the process of harden test. As you can see in the middle of the uh, middle, and then from the surface is can produce a very different, okay, different hardness. Okay, in case of the quenching oil, okay, by using the oil quenching at the same this the same alloy, but the diameter is different, you can see the curve is something like this. So for the uh, 50 mm can produce very uh, higher hardness if compared to the 75 mm. Okay, if compared to the different alloy, okay, at different alloy at the same diameter, okay, quenching in water for the 4140 is basically higher if produced to the 1040 is due to the different carbon content. Okay, so for the specimen size, basically effect for the hardness. Okay, when the specimen is bigger, it will produce a hardness is very less to the uh, smaller diameter. Okay, and then we proceed for the cast iron.